In this video, we're going to discuss some diagnostic measures on our linear regression equation. So far, we figured out how to form the equation. We figured out how we can actually get those estimates of the slope. And we know that that is the best equation possible, the best straight line equation possible. But there's another question that needs to be asked. Is it any good? You might say, well, it's the best one. It's got to be good. But that's not necessarily true. Maybe it's the case that there aren't any good equations and there aren't any good lines that we could do. So we need some way to quantify how good it is, how strong that relationship is. And we have correlation, and that's great. That's one way we can determine how much of a straight line it is. But when we start thinking about multiple x's, it's going to be very difficult to quantify how good, instead of saying how I can use height to predict weight. What if I want to use height and age to predict weight? Well, those correlations, there's a lot of stuff that's intertwined, so trying to describe how good the relationship is quite difficult. Our two major diagnostic measures that we're going to focus on will be the R-squared and the S, or the RMSE, stands for root mean squared error. Let's start with R-squared. R-squared is usually one that's been discussed before. R-squared is simply a measure of the proportion of variation explained by the line. And we're going to see in a couple slides exactly what that means when we can visualize it. But really, you can think that the higher values would be better. We call this the coefficient of determination. It's just a measure of how well our line does in predicting, essentially. We do know that larger values of R-squared means that the points are closer to a line. And one thing that I do want to make clear is that there is no universally defined scale on what a good R-squared is. I always have students that come and say, well, is this good? Or this R-squared is not good. It's only 40%. Well, a lot of times we get into textbook examples where magically in the textbooks, all the data sets follow these great R-squares of 80%, 90%, and we can explain a ton of stuff, and that's just fantastic. And then people go off into real life and they say, oh, I only have an R-square of 40%. I must be doing something wrong, or there must be something that's an issue here. And it turns out that's not true at all. It turns out that in the real world, in the wild, R-square of 30, 40% might be the best you can do. I mean, there are some cases where you can get in the 80, 90% range. But there's no way to say, oh, this is good, this is bad, or this is high enough. Well, high enough is variable. There's nothing that says, well, once you get above 50% R-squared, then you're okay. Not true. You can have plenty of examples of 30% R-squares that are good regression lines that help you learn or predict better. So again, let's start by thinking about how to get this R-squared value. So the measure of goodness of fit we're talking about here is the R-squared. I said it's the percentage of variation of the dependent variable explained by the regression. Now remember, we talked about this sum of squares idea. And we said, okay, we want to minimize the sum of squares. Well, really what we're doing is we're saying that if you didn't consider x at all, so you did that really simple model with a flat line is what it actually will turn out to be. You say x doesn't matter. Well, how much error does that have? How much error does that first very simple line have? And in fact, I'm going to slip to the next slide here and say, what if instead of the blue line, I use the red line? The red line is telling me x doesn't matter. Because it's saying, oh, well, this is a case of predicting beer sales based on the temperature at a baseball game. And you could say, well, as the temperature goes up, the red line says the sales are the same. So if that's the case, then who needs to know the temperature? It doesn't matter. I'm going to sell the same no matter what. But my question is can I do better with the blue line? And certainly you see the dots on there. It certainly appears that the blue line fits those points better. But how much better? Well, the idea is I'm going to say, what percentage did we reduce our error by? Well, what we're going to do is we're going to look at the error, the sum of squared error, for the flat line, for that red line. If I summed up the squared residuals for the red line, I actually call that my sum of squares total. How far away are the points away from the average, and I'll square it. That's my sum of squares total. And sum of squares error, SSE, was what we talked about in the last video. Literally looking at our best line and saying, well, what's the sum of the squared error values? And that should be smaller, because if you're saying the best line is the blue line in that last graph, well, that should be better than a flat line because it's the best, so it has to be better than anything else. So I should have less error. But the question is, how much less? What percent less? Well, that's SSE divided by SS total. That's how much error remains after I put a straight line through the model, the best straight line. I've taken it from, here's how much error a flat line gives me, to here's how much error my new fancy line has. And hopefully, it's very little error left. R square says, what was the drop? You started at a certain amount of error with the flat line. You dropped to lower error with the tilted line. What percent did you get better? Did you get lower? That's our R square. And here's an equation, 1 minus SSE over SS total. We can see where this comes when we start looking at some output, but you can actually visualize that in the summary of the model. Couple things you should know about R square. It is always between 0 and 1. Cannot have an R square above 1, cannot have a negative R square. The closer the R square is to 1, the better the fit. Because if I've explained 100% of the variation, R square of 1, that means there's no error left. I've explained it all away. The straight line I put through was perfect. And if it was perfect, I've explained it all, and that's a perfect fit. Now you might say, wait, R, we've seen R before. Why do you use R square? Well, guess what? In simple linear regression, it literally is R squared, because R from week 2 was what we used to represent the correlation. Therefore, R square is nothing more than the square of the correlation of x and y. So a negative 1 squared gives me an R square of 1. A 1 squared gives me an R square of 1. So it's basically saying I don't care if it's a positive slope or a negative slope. They both explain all of the variability. The sign doesn't matter anymore. The higher the values of the correlation, closer to +1 or closer to -1, the higher the R squared gets. And that should make sense because that means the points are closer to a line. The benefit is not necessarily in this 1x, 1y realm, this simple linear regression. The benefit we see from this new definition of what percent of variability is explained, that comes into play when we get to multiple linear regression. But let's go back to our example here. So I'm predicting the number of beers based on the temperature. And I say, well, here's the best line that's flat. So that basically says X doesn't matter. Temperature doesn't matter. And from here, I could say, well, let's look at this particular point here at about X equals 77. This is my best flat line. This is my best line of any type. We could say, you know what? Remember I called it sum of squares total? I could say, how far away is this point from the best flat line? yi minus y bar. That's the total variability. And I could say, well, I can break that into two pieces. I can say, how much error is there from my best line? This is my residual. We called it the residual. How far off the best line are you? And then how far off is the best line from the flat line? Notice what I'm doing, we call it partitioning. Because I'm taking this total deviation, how far away a point is from the flat line, and I'm splitting it into two pieces. One is the error that I can't get rid of. This is the error that stays around. This is the error, even if I do a better line, I still have error. But I did explain away and get rid of this part. So we talk about signal and noise, fit and error. Even with the best fit, I still have error, but the best fit is better than a reduced fit. And the reduced fit here would be what if I just ignore temperature? Reduced fit says ignore temperature, flat line. If you include temperature, I seem to get a better line. How can I get a number to quantify how much better? That's the R square. Another measure I can use is the standard error of the estimate. Well, the standard error of the estimate is also called the standard you'll hear the standard error, you'll hear RMSE, which stands for root mean squared error, and they all mean the same thing. Really all it is saying, you see that the points, even here, forget about all the different highlights, just look at the blue line. And you say, well, each point has a certain residual from the blue line. They're not on it, but they're around it. Those are my errors. So if I say, what's the standard error of my errors? I could simply say, give me the standard deviation of those errors, essentially. How spread out are those errors? I hope that they're small, because I would expect that on average I'll have some above and some below. But I'd love to know how tight they are to a line. For example, if I'm trying to predict the number of beers, I might say, oh, when the temperature gets warm, I can predict you're going to get more beers. And you say, well, how much more? You say, well, at 90 degrees, I think you're going to be between 20 and 50,000. Between 20 and 50,000, that's a huge range. That's a big spread. This time, it looks like these points are pretty close to the line. So maybe I can predict, oh, up here, it'd be reasonable to say maybe between 32 and 37 would be my best prediction. Where did I come up with that? Well, I just picked a little range around the line. How big of a range do I need to pick? Well, that's a good idea of looking at the standard error. Now we have a formula for this. Honestly, we're really not going to use it. But the idea is simply calculate the standard deviation of the residuals. And in general, the standard error tells us how close the points are to the line. The standard error, if it's low, that's good, because smaller standard error means the points are tighter to the line. They come closer to being on the line. If it's bigger, it's saying, well, we're not really sure how far out it goes. It can be fairly widespread. That gets into that idea of what is good versus what is best. This is the best fit line, but is it good? We got to check that out. If it's a best fit line and it has a huge standard error, that's not very good. And there might not be a better option, but that's how good we have it. If we assume the residuals are normal, which we traditionally do, we can use the empirical rule when we look at the residuals to find out where are the current quote-unquote outliers. Remember, standardized residuals should lie within about, or residuals should lie within about 3 standard errors, 2 to 3 standard errors. If you see a residual, an error that is 5 standard deviations above what you expected, that's pretty weird, and I might want to look into it a little more. Really quickly, I want to jump back over into R, and I want to look at this CARS model that we made, and I'm going to look more specifically. Actually, I'm not going to type anything. I'm going to come down here and look. And you see in the output, you see it says here multiple R square. That's really just our R square term, 75%. So if I know the weight, I can explain away about 75% of the variation in miles per gallon. In other words, miles per gallon goes from about 11 to 34 in our data set. If you tell me the weight, I can get a lot closer than 11 to 34. Maybe I can say, oh, well, I can get between, for this value, maybe between 13 and 20. Maybe it's not great, but it's a heck of a lot better than 11 to 34. You also see a thing that says residual standard error. That's our S. Another way to think of that in a quick term is to say, this is quick and dirty. This is not precise. But if you say, I want to predict in this case, if the car weighs 4,000 pounds, I think the 4 stands for thousands of pounds, give me a range of values of what you would likely think. Well, I could plug 4 into the equation and get my best prediction. And then I could say, well, you know what? That standard error says, how much should I bounce around that fitted value? And you say that, 95% of the time we're within 2 standard error. So I could say, you know what? If I go to this line equation, plug in 4, I would get about, let's say 16. That would be my prediction, 16 miles per gallon. But it says here the residual standard error, if you go up 2 standard deviations, down 2 standard deviations, it's basically saying, okay, 16 is my best guess, but it's probably between 10 and 22. That should give me about a 95% confidence interval. Once again, it's not perfect, but it's an eyeball test, and we can use that standard error to get an idea of the variability. In the next video, we're going to look a little bit more deeply into residuals and how we can use them to check our model assumptions.